Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, February 24, 2023. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a clear and frosty winter's evening in my hometown of Rockport, Massachusetts. These Earth and Space Reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environments, and who wonder about the greater cosmos and all that it contains. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I am grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry Earth and space scientists and communicators, far-flung friends, family, and other curious folk. Thank you for your comments and encouragements. This evening, we will be treated to a timely presentation by Dr. Sean Linden, who will talk on finding buried treasures in nearby galaxies with the James Webb Space Telescope. Dr. Linden received his PhD in the spring of 2020 from the Department of Astronomy at the University of Virginia, working with Dr. Aaron Evans and Dr. Eric Murphy at the National Radio Astronomy Observatory. He is now a postdoctoral researcher at the University of Massachusetts in Amherst, working with Dr. Daniela Calzetti on studies of star clusters in nearby galaxies. In the fall, he will be starting a 3-year fellowship in the Department of Astronomy at the University of Arizona. He and his collaborators are currently working hard analyzing data from the James Webb Space Telescope Early Release Science Program. When Sean is not doing science, he is an avid hiker around New England. I first saw Sean talk about his work with the James Webb Space Telescope at a regional meeting of the American Association of Physics Teachers that was held this past November at Worcester Polytechnic Institute. In his presentation, he showed amazing images from the Webb telescope that revealed star-forming galaxies as never before. I knew I had to get him to come talk here. Fortunately, he agreed. And so, Sean, welcome to this gathering of fellow astrobuffs. The platform is all yours now.
Wow, thank you so much for the introduction. It's a pleasure to be here, be with you all tonight, and just get the opportunity to talk to you about some of the work that I've been doing here at UMass and will continue to do with the James Webb Space Telescope over the next couple of years. So let me, I guess, share my screen.
Looks good.
See if I can switch into full mode. How does that look?
Perfect.
All right. Yeah, so as Bill said, I'm going to talk to you today about finding buried treasures with the James Webb Space Telescope. And I decided to start off with a little bit of new results about what's been discovered at some of the high redshifts. So while my work and most of the research that I will talk about at the end is focused on nearby galaxies like the one you see on this title slide, I'm going to talk a little bit about some high redshift stuff in the beginning as well, because the early release science programs are constantly taking data and releasing new results. And every time I get an opportunity to talk to people, I end up having to, talk about 3 or 4 new exciting results. So I can't help it. I'm going to spend a little bit of time on that in the beginning. But to motivate the James Webb Space Telescope, I like to show this image comparison between the size of the JWST primary mirror and the size of Hubble. Now, Hubble has actually been up in space for the last 30 years. It is by far the most successful space mission in the history of astronomy. Maybe the most successful mission in the history of astronomy, arguably. And you can see just how much bigger, how much more collecting area the JWST mirror has. And it has this funny shape, actually, which results in a kind of funky looking point spread function, which is what the light actually looks like from a very, very bright object. And you'll actually see examples of what I'm talking about in a second. But what the power of the Webb telescope is that it allows us to look not only in the infrared, but also very, very far back, because it's so much more sensitive than Hubble was. So for infrared light, of course, what the infrared is telling us is things that are essentially hidden in the optical. The infrared, from a human's point of view, gives off heat. And you can see just the images on the left. If I put a paper bag over one's arm, you can't see through the bag in the visible light, like what you see here in Orion. But if you have infrared glasses or an infrared vision, you see that you can actually look right through this bag. And the bag here is a metaphor for the dust that lives within galaxies, between galaxies, around in the universe. And so on the right-hand side, I'm showing the exact same image of Orion, but in the infrared. And you can see that Orion is not simply a collection of a couple of bright stars. It actually represents this massive complex of star formation and dust that's interweaving and connecting around the entire system. These very disparate points that just look like individual stars are actually woven together in this mesh of dust and gas. And you can actually see that very well in the infrared. So the infrared not only allows us to, it looks through dust, it changes our view of the universe, but the Webb also allows us to look further. So but the combination of those two things means that the James Webb Space Telescope is probing further back in the history of the universe than any other telescope. And part of the reason for this is that as galaxies get further and further away, their light gets redshifted. And so here I'm showing an example of a nearby galaxy on the left-hand side, the very left panel. And as you step the panels through, as you redshift the galaxy, this galaxy on the left would actually appear as a very, very high redshift red point if it were formed at the early part of the universe. And so what we're looking for in these big mosaics of galaxies that you may have seen is these super, super, super tiny red dots. These things are bound to be the highest redshifted galaxies, which allows us to look further back in time and get as closer and closer to finding galaxies that formed right after the Big Bang. And this is important because we still have a lot of unanswered questions about how the universe evolved from that early time right after the Big Bang until today. And the only way we can really figure that out is by finding galaxies at those early times. And so Webb is going to be able to, and has already actually found many of these blobs. And here is an example of one such result. Actually published, I think, 2 weeks ago or a week ago. One of the early JWST teams released an image of the Goods South Field, which is a legacy field that Hubble actually had spent probably thousands of hours imaging in every single wavelength available to Hubble. And JWST is similarly covering it. And we can see that all of these very, very red dots that have been identified, zoomed out here, are all at redshifts between 11 and 13. And actually the highest redshift galaxy we ever discovered up until a couple of months ago was at a redshift of 10. And so now we're actually finding and confirming galaxies at a redshift of 13, which is only a couple 100 million years after the Big Bang. So we're really now starting to finally collect real life examples of objects. What I showed you in the previous slide of galaxies was more or less a cartoon, what it might look like. These are actually real objects that we're detecting now for the first time. And it's important to note that these are so red that they would have been completely invisible to Hubble. So it's not that they're so dusty, it's that they're so redshifted that their light is essentially falls outside of what is visible with Hubble. And so only something like JWST would be able to find these things. And you might say, well, why couldn't Spitzer, a telescope as in the infrared as well, a space telescope, find them? And that's because Spitzer had such a smaller mirror. The collecting area was so much smaller, it was not sensitive to these very, very, very high redshift galaxies that have very little light that's getting to us. Okay, so zooming all the way back, I talked about how JWST can transform our view of stars and galaxies. And I like this cartoon because it shows kind of what the life cycle of a star is and where JWST can fit in different parts of this life cycle. So on the top is our sun, or a star like our sun. And as that star is going to evolve, it'll turn into a red giant. And eventually the red giant will shed its outer layers and be left with what is called a white dwarf, with surrounding shells of gas that lived in the atmosphere of the red giant. And then if the star is massive, so much more massive than our star, it would potentially end its life as a supernova. And if it's very massive, even a black hole or a neutron star. And what I want to focus on today is actually the birth of stars. So focusing on the star-forming nebula. And one of the famous early images that came out of Webb was this sort of cosmic cliffs. So I want to show this image again and play this movie, which actually gives you the context of what you're looking at when we talk about the cosmic cliffs. The cosmic cliffs are actually the rim of a larger nebula, which is powered by a couple of bright stars, which itself lives in a larger, greater nebula called the Carina Nebula. So the cosmic cliffs, and I'll just let it play again while I talk, are a very, very zoomed in portion of a larger star-forming complex. The complex itself probably has thousands of stars that are forming. And you can see now with JWST, what we're mostly finding is all of these stars kind of lit up in bright yellow. You sort of see littered and red, littered across the cliffs. And these are things that were completely hidden to us behind the dust. And so now with JWST, the dust veil is lifted away, and we can see all of these bright stars forming in the cosmic cliffs. But these are not these extremely massive stars. They're sort of these lower mass stars that are kind of hidden in the sort of rim of dust that's been pushed out like this because of the very bright stars that formed at the center. And so like we said, when a star like our sun turns into a red giant, it pushes that material that can go on to form new stars out into a nebula. And so now you're seeing the rim of one of those nebulas and new stars being formed within the rim of the ejected material of another star. And so this is, again, recycling feedback within the interstellar medium. Within our galaxy, gas is recycled, reborn, renewed, recycled. And you can see I talked briefly about the funky pattern of the JWST mirror. That actually is what causes these hexagon-like stripe patterns. In really, really bright stars that saturate the detector, you'll get these sort of weird kind of cross patterns. And that's due to the shape, the kind of funky shape of the hexagons. Okay, so moving up a bit. So what I just showed you is a sort of a lower scale nebula with a couple of stars that are powering most of it. What I'm showing you here is something much, much different. So this is the Carina Nebula. And the Carina the Tarantula Nebula. And the Tarantula Nebula contains a star cluster called 30 Doradus. This is a star cluster in the Large Magellanic Cloud, or the Magellanic Cloud system, that is actually contains 500,000 suns. So it has a mass of about 500,000 suns, all packed together in this bright ball of blue points that you see. Each one of those is a star. And there's 500,000 of those compacted together to form what we call a star cluster. And this is one of the most massive star clusters that we know about in our very close by universe. And so this is actually a JWST image of the 30 Doradus star cluster. And what you see in red and sort of piercing through the entire region is all of this gas and dust that is gone and been pushed away by the star cluster as it's formed. And this was the material that seeded the birth of that object behind all of that sort of dust layer. So with JWST, we want to find more examples of these dense star clusters, which do a lot of work to recycle material out into the galaxy and cause galaxies to evolve. So one such project that is doing this is the Physics at High Angular Resolution in Nearby Galaxies survey, or FANGS. FANGS is a program that has about 30 nearby galaxies, but the point is that they have star formation rates that are higher, a little bit higher than the Milky Way. And so while most of them are sort of normal spirals, we're still able to find thousands of these 30 Doradus-like objects. So we only have our 130 Doradus in sort of near us. These galaxy surveys like FANGS allow us to find thousands of these 30 Doradus-like sources. And what the movie that is playing is actually flipping through a comparison of what HST and JWST see for the galaxies. So what you're seeing here is the Hubble view. And then when it flips, what you're seeing is all of that gas and dust being lit up by JWST. So again, all of these sort of bright, dusty regions that have lots of stars and star clusters are very easy to detect with JWST. And so the problem is, and so where my research comes in, is that spiral galaxies like that one I just showed and the Milky Way, they are not representative of what these high redshift galaxies are actually probably like. So while the highest redshift systems really only look like red blobs, if you had enough resolution, a lot of them actually look like these high redshift blobs are mergers between multiple galaxies at a time. And so while we don't have the resolution to resolve individual galaxies at, redshift of 13, we can only detect, a couple of bright pixels at a redshift of 13. We think that a lot of these really early redshift galaxies are undergoing lots of mergers. And so if we want to understand how 30 Doradus-like objects form in galaxies at these really early redshifts that were high redshifts that we're now starting to discover, we need to be studying systems in the local universe where we have all this detail that are representative of these mergers. And so spiral galaxies like the ones in FANGS are not representative. We need a sample of galaxies that we can study in great detail that we think actually looks like something that you find at higher redshift. And so I just want to show what a galaxy merger looks like in a sort of state-of-the-art simulation. These simulations are primarily using gravity, but they're also simulating the gas and the dust and new stars forming. And that's why you see the galaxies flickering. And just there, you see as the two galaxies come through, all of that sort of dust you see is being ripped out of the two galaxies. And all these new stars are forming as a result of that. And eventually the galaxies will coalesce together and form a single object. And we think that this is happening a lot at high redshift. And so to solve this problem, my collaborators and I have undertake the what we call the Great Observatory's All-Sky LIRG survey. This is actually the brightest 200 infrared bright galaxies in the local universe within a redshift of about 0.02. So we're talking about galaxies at redshift 13, and these galaxies all live within a redshift of 0.02. Now, it turns out that these mergers are very rare in the very, very nearby universe. So there's only 200 of them. And when we point Hubble at them, we find that many of them, nearly all of them, are mergers of these two massive disk galaxies. And you can see from this montage of only a fraction of them that we find them at every single interaction stage. We find things as widely separated pairs. We find things as close, about to merge. We find things as almost completely merged single galaxies with tidal tails that you can see fading away. And these galaxies have star formation rates that are 10 to 1,000 times higher than what we see in the Milky Way or what we see in the FANG survey. So GOLS is able to take the conditions of high redshift galaxies, where we can only just hope to detect them. And don't get me wrong, detecting them is incredible. But now we can say, well, we're going to study these kinds of systems in great, great detail in the nearby universe. And so NASA awarded us time in the early release science program to study 4 of these luminous infrared galaxies in GOLS. And so this is actually where a lot of my research has been focused on over the last 12 months. And there are 4 galaxies here: NGC 3256 on the left, JWST 96, NGC 7469, and VV114. Now, I just want to quickly point out that NGC 7469, the reason that you see a galaxy here with these bright, sort of cross-like pattern, is because the center of this galaxy is a black hole, a very, very bright black hole that's actively both pushing material away from it and eating new material. So that active galactic nucleus is the main reason that this galaxy was chosen, because the beauty of galaxy mergers is that not only when the galaxies collide do you get lots of star formation, but you also get black hole activity. And so the GOLS group is made up of lots of people. Some of them are very dedicated to studying black holes and feedback, and then others are focused on studying the star formation properties. And so this is a galaxy that I'm not going to talk about today, because primarily the research is focused on black holes, though I'm happy to talk about it a little bit at the end if you'd like. The other 3 galaxies here, actually, I'm going to talk about them in order of distance. So the furthest galaxy away is JWST 96, and then VV114 and 3256. And the reason for that is because you can sort of see, actually, these are JWST false color images of these 3 galaxies. So again, the redder material is sort of where the gas and the dust forming around these really young star clusters is. And so you can see right away in JWST 96, nearly the bulk of all of the emission in this galaxy is coming from this very, very compact, bright region off to the sort of middle left of the image. And so JWST 96 was chosen for our ERS program because this region, previously identified by Hanai Inami and in 2017, that this region D1 that you see in this inset on the left-hand side actually makes up the bulk of the infrared emission for this entire merger. And there is potentially 3 or 4 galaxies individual. So you see the one off to the far left and then the 2 off to the right. There's 3 galaxies, maybe more, merging in this entire system, and most of the infrared emission is coming from this tiny, tiny region labeled D1. Now, I showed you what Orion looked like. Now, if you take the surface density of Orion, all the stars that are forming in there, which is the closest massive star forming region to us, this region has a surface density of infrared emission that is 10 times higher, which means that you would have 100 times of the density Orions packed in to a region like D1. And actually, with just imaging alone, the region is so compact and is so red that we cannot actually distinguish whether or not this region is mostly stars or if there is a black hole sitting at the center. And actually, that's why you see that 2023 in prep, we now also have spectroscopy of this region. And that's actually going to be the final definitive evidence whether or not this massive D1 region is a black hole or just a really, really massive star cluster, a 30 Doradus on just steroids. Okay, so VV114 is actually the galaxy that I have primarily been worked on in the fall. So on the left-hand side is the Hubble image of VV114, and you can see it's a sort of tale of two galaxies. The northern system is pretty visible in the optical. You can see all those bright star-forming regions in sort of pink and blue. That is where there's really very little dust in the merger in that region. Now, if you look to the south, or what is VV114 east, because these images are sort of flipped on their sides, you see that the other galaxy is completely enshrouded in dust. We do not see anything. We do not see any stars forming anywhere near the eastern galaxy, or the eastern galaxy. Now, moving from Hubble to the near infrared with JWST, we see that not only are we detecting dust in and around these massive star-forming regions, so where we found massive stars forming before, like Orions or 30 Doraduses, we find the dust that gave birth to these stars, the gas and the dust that is sort of surrounding them. And then all of a sudden, we see that the dust lifts around the eastern nucleus. And what we see is actually a black hole at the center of the eastern nucleus that is causing this bright sort of, again, this sort of PSF point cross-hatching. And so that was actually a new discovery. And we had a series of papers talking both about all of the star clusters that are forming in the dust and then the black hole as well. And actually, you can see now with MIRI going even further into the infrared. So now from the near infrared on the left to the mid infrared, which is around 5 to 15 microns, whereas the near infrared is about 1 to 5 microns. You see again that we find these massive star-forming regions lit up in purple and pink. The bright AGN nucleus is there. There's actually two really bright sources in there. We think only one of them is a black hole and the other one is actually a bright star cluster. And you see in blue all of this diffuse dust. This dust has been pushed out of the galaxy as the merger has progressed. So if you remember that simulation that I showed you, and when I slowed it down and you saw the dust getting ripped out of the galaxy as the two nuclei came together. What you are seeing here on the right is a real life example of that movie. I mean, this is real data. You can see the blue, the dust is being ripped out of the galaxy as the two nuclei merge together. And so we've never been able to take sensitive high resolution pictures of these kinds of galaxies before. Spitzer and Herschel never had the sensitivity. And so this is all completely new and sort of showing us that we there's more to these emerging systems than we even thought was there. So now focusing on the work that I did specifically, we wanted to identify, again, all of these super dusty, buried star clusters, these 30 Doraduses. Now, the thing about mergers is because mergers have star formation rates that are 10 to, again, 1,000 times higher than things that I was talking about in FANGs, it means that the star clusters that are formed in these galaxies are way more massive. So 30 Doradus is 500,000 solar masses. We are getting star clusters in these systems that are 10 million solar masses. So much, much heavier, more massive. And we think that these are the kinds of star clusters that are forming in those really high redshift galaxies. So if we can find these kinds of objects, detect them, characterize them, understand them, then we can hope to understand something about those really high redshift galaxies that we cannot resolve into individual components because they're too far away. We can just, again, hope and be happy to detect them. So now I'm going to show you a movie of the HST and JWST images. So the HST, again, now we've rotated the galaxy back to the east-west sort of view. And you see with Hubble that the eastern nucleus is completely dust enshrouded. But what I want you to focus on is sort of where my cursor is, the middle of the between the two nuclei. You see that there's about 10 or so really, really bright red objects that sort of pop out in the infrared. And you see some as well along this spiral arm and woven again through between the overlap region between the two nuclei. These extremely red sources are the sites of these extremely massive dusty clusters. And these are where all of the youngest stars are forming. And what is powering the bulk of the infrared emission is the dust and these bright red objects. And so we're only now able to find these objects for the first time. We completely missed them in the Hubble images. You see that in the Hubble images, there are these faint red sources that we really have no hope to characterize, because the problem with understanding these objects is that we have to look at them across their multi-wavelength observations. And so we cannot detect clusters like this in the ultraviolet. And we previously relied on the ultraviolet to give us a handle on how old the object was, so that we could say something about sort of when the star cluster formed and where. And now with JWST, not only can we find these things that were completely invisible in the UV because there's too much dust, or the optical because there's too much dust, but we can actually use the near infrared part of the spectrum to tell us something about the ages of these objects as well. So we can both detect and characterize these extremely young, massive clusters in these galaxies. And so my paper revolved around essentially finding these previously unseen sources for the first time. And I just wanted to say the next step is what we're working on now. What I was working on, 30 minutes ago, is the nearest galaxy in the set of 4, which is NGC 3256. And the reason that it's so great is because as the galaxies get closer, we get even more detail. So even within our galaxy survey, we have galaxies at, the Zwicky 96 was at 100 megaparsecs, which is, can never remember the conversion to light years, but the Andromeda is about 1 megaparsec, so, or less. So it's like 100, the Zwicky 96 is about 100 times further away than that. VV114 is at about 80, and then NGC 3256 is at about 40. So at 40 megaparsecs, it's one of the most nearby galaxies in the whole GOAL survey. And you can see that we detect not just one really bright source in Zwicky 96 or 20 or so bright sources in VV114, but here actually we have thousands of bright red young clusters forming in the galaxy. And so this is the sort of window. And so on the left-hand side is the HST image. where again, you see the white arrow is pointing to a region in the galaxy that is completely hidden by dust. You see that this massive dust lane sweeping across the galaxy. And on the right, you see that actually what is behind that dust is another nucleus. So when the two galaxies are merging, the northern nucleus is visible out in front of the dust, and the other one is completely hidden. And so now we're able to actually detect both of them and characterize them for the first time. And that's what you're seeing on the right-hand side with the near-infrared JWST image. And so this is really where we're going. And this is just really the beginning, because the idea is what we want to do is not just find these super young sources, but we want to understand how their actually feedback takes place. And so one of the things I alluded to, and I'll briefly go back to it because it's sort of relevant to the physics, is you see that the gas and the dust gets pushed away from these star clusters. And that's because of feedback, either through winds from massive stars or just photoionization, just the actual photons moving out, or photons that are absorbed by dust and then re-radiated in the infrared, and then those infrared photons, again, pushing away more gas and dust. And so this feedback cycle is crucial to understanding how galaxies evolve. When I showed you that movie of the two galaxies merging and the stars lighting up and the gas moving around and going on to form new stars, all of that can only happen because of some prescriptions, that idealized models that we have for feedback, for condensation of new material, for these kinds of processes. And you can see that it's not a simple circle or a sphere or kind of an idealized situation. Even just one example, 30 Doradus, is this complicated weave of gas and dust that doesn't look like a very symmetric shape. It doesn't have a very easy structure to kind of tease apart. These are very complicated objects. And so what we want to do is, once we can find these super red clusters in these nearby galaxies, we can then attack them with spectroscopy. And spectroscopy allows us to understand not only where they are, but the energetics of the region itself. So we can understand how the material around the cluster is moving. And that actually gives us a sort of a 3D picture of what's going on around these star clusters, which then allows us to understand how the feedback is working. And then if we understand how that physical process is happening in these kind of extreme galaxies, then we can take that to our galaxy simulator friends and we can say, okay, we actually think the high redshift galaxies evolve like this with these kinds of inputs. And the more nearby galaxies evolve differently. And then you can actually build a realistic picture of actually how galaxies evolve throughout the history of the universe. And so that's kind of where we're hoping to go. And that's kind of all I have. So happy to take any questions. Looks like there's a few in the chat. Thanks for listening.
That was super. Let me get the gallery back. There they are. So welcome some questions from the crew here.
I have one quick one. That's all right. The 30 Doradus cluster, I've never heard of anything other than a globular cluster having that many stars in it. Obviously, I think it's obvious we don't find globulars in nebulae like that. Are they also very bright to the Webb in very high redshift galaxies? And have we discovered anything about their formation that we didn't know before?
Excellent question. Yes, globular clusters are very interesting. They're also very easily to find with Webb. They're mostly made of old stars, but you're right, they have millions of stars in them. And you're right, we do not find them around nebulae. And now there's a lot of actual interest in recent research about the globular clusters that we find in the Milky Way, in the halo of the Milky Way. We think a lot of them actually formed with the Milky Way. As the Milky Way is evolving, they sort of formed and got kicked out, and they sort of live out in the halo, and they evolve, and they get older, and they stay out there. We also think some of them are the remnants of galaxies that were brought in. So you see, globular cluster, what a globular cluster is versus the sort of core of an old dwarf galaxy. The line is actually getting somewhat blurred. But Webb is able to find them, and not only is it able to find them in all of these nearby galaxies, but we're actually able to find globular clusters in high redshift galaxies. So one of these exciting results that came out, and I don't have an image of it, I wish I did, is, and you can look it up, it's the sort of cosmic sparkler. It's this redshift 4 or 5 galaxy that is edge on, and in the halo of this edge on galaxy is all of these globular clusters detected with JWST. It's incredible. And so it allows us to actually understand that many of the globular clusters that we think the Milky Way has were probably in place a long time ago, and that they've been evolving with the Milky Way for a very long time, which again is this sort of new area of open research. Is when did all the globular clusters come in? When did they form? How did they form? And so, yeah, we have learned a little bit now about globular clusters, and there's going to be even more intense research focusing on specifically targeting lensed galaxies, hoping to find globular clusters with Webb that we could not find with Hubble because of the resolution. Is we can go to these super magnified systems like things like Einstein rings, and the galaxies are magnified so heavily that you can find globular clusters maybe even in redshift 6 or 7 galaxies. And that really would tell us a lot about when the first globular clusters formed, because right now it's kind of really only theory.
Mario,
very
has a
cool.
question.
Thank you.
Okay, my turn. I think William was in front, but okay. You actually may have just answered what I was going to ask, which is there any evidence of the date of formation of the globulars compared to the cores of the actual galaxy? Because we know that the globulars are one of the oldest stars in the sky. So I was wondering if there was any direct evidence that the globulars formed early and then got incorporated into the galaxy. You mentioned the sparkler galaxy.
Yes, yeah. So the sparkler is probably now some of our best evidence. There's been a few others that have, again, come from some of these highly magnified lens systems. The sparkler is probably one of the now best direct image examples of witnessing clear evidence of globulars at high redshift. One of the other things that is of intense research is, instead of finding globulars in higher and higher redshift galaxies, what you do is you study the heck out of the globulars in the Milky Way to not just figure out when the oldest star in the cluster formed, but how, if there were multiple generations of star formation happening. So these objects are so massive, and it potentially takes a long period of time to actually collect and form 1 million stars. And so it could be the case that they all kind of form at once and evolve as one single thing. It could be that some of the globular cluster forms at one time, and then some of it forms at a later time. And then that might actually tell you something about globular cluster formation as a whole, and what fraction of globular clusters have these kind of bimodal age distributions. It turns out that if you look really, really, really deep with Hubble, you can find a couple examples of these kind of weird multi-age spread globular clusters. And by multi-age, I don't mean like, 10 billion years and 100 million years. It's like, things that formed at 10 billion years and then again at 8 billion years. So still very old, but there is a sort of lag when some of the stars form. So we're still trying to learn more about that. And Webb actually allows us to go to even lower mass stars. And so, not only is Webb able to tell us more about high redshift globular clusters, but it can look at the ones in the Milky Way at even higher detail than Hubble. And so that's also being done.
So Tony has a question, and I just want to note that as Tony noted in the chat, that he's going to be working on JWST data as well. Okay, Tony.
So yeah, I have a question, a comment. The comment is, first of all, I guess back to your the Tuzwicki 96. I just want to say there was a beautiful spiral. I'm guessing like a SC morphology galaxy in the southeast corner that appears on the JWST and not on the Hubble. That's amazing to me. That there was another image that showed that more, I think. Or was that VV146 114? Two slides. Yeah, that one right there.
You mean this guy right here?
Yes.
Yeah. So actually, I love that you pointed that out. So one of the things that was a challenge actually when we were writing this paper at the end of last year was we found all these super red, bright red things, and we think, oh, this is great. You know, look at all these clusters. And we had hundreds of them in the beginning. And you know, you might say, well, how do we get down to only 20 or so? Well, that's because a lot of them, when we went and we looked at them in detail, are actually galaxies. And you see, there's one right there. There's two more right there. There's another one there. There's one right there. There's 4 or 5 right there. There's so many galaxies. There's another 6 or so over there. There's so many galaxies in these images. And we are just looking at nearby galaxies. We weren't trying to find those high redshift galaxies. We didn't know they're there. It's a consequence of the sensitivity of Webb. And it has been, other people's, my annoyance is other people's science in that sense.
Is the sensitivity or the dust obscuration there?
Well, it's probably a combination of both. Like this one that looks really red, that's probably a sensitivity thing, is that Hubble is not really sensitive to that galaxy. Whereas you see these two, this and this galaxy and this one right here. You sort of see them in Hubble, but there's just a lot of probably dust in there. And so you see them a lot better with Webb. And so, yeah, it's kind of a combination of both sensitivity and dust.
Yeah, that's so cool. And my actual real question was, so as Bill mentioned, and Bill, that was a comment just to you, by the way, but so I worked with Bill back at Tufts a number of years ago, and I will actually be resuming grad school to finish my PhD, and I'll be using at University of Wyoming with Danny Dale using the FANGS collaboration data. So I am
awesome.
I'm super excited to see what you're seeing here, you know.
Yeah, that's amazing. Yeah, so you're starting in the fall then?
Yeah, we can chat later over email, but my specific question was what like software programming paradigms have you used for this mainly, and what would you encourage for someone like in my position here?
So FANGS has their own set of things that they have done. Well, actually, one of the people that developed kind of this technique called a watershed algorithm, it sort of is it's a dendrogram analysis of images that sort of breaks things into sort of fractal substructures. That code was actually developed within FANGS by one of the former Bowles postdocs. So there's a lot of cross between all of these groups. But besides that program, one of the things that we've used in GOLD and other people use in Nearby Galaxies is source extractor. And so source extractor is essentially an algorithm that looks for continuous pixels on an image. So if you imagine that these are false color images, if you were to look at the real data, it's all just individual pixels. And really what source extractor is doing is it's saying, you give it a set of parameters. Let's say I want 3 pixels together of a certain brightness, you call that a new detection. And then if you give it, loose enough parameters, it can find, anything. And the sort of magic there is kind of playing with the parameters to get kind of it to detect the things that you want it to detect. But yeah, of course, happy to talk about it over email.
Yeah, let's do that. And that's previously known by a different name, right? Source extractor.
Yes. Yeah.
So I have a question about the emission itself. You have, what is it, between the two cameras on Webb, the near infrared and the mid infrared, you have, I think, 6 bands or so, typical. And
Yeah.
so you have very crude, spectrophotometry.
Yeah.
Is that enough for you to be able to discriminate between emission by dust that's been warmed and emission from molecules, emission by molecules such as polycyclic aromatic hydrocarbons?
Yeah.
Can you discriminate between that and how much of each you got?
Yeah, that's an excellent question. So what we have, so there's about, I think, there's about 12 NearCam filters. So there's quite a lot of, well, not a lot, but there's about 12 NearCam filters. It's a
Mhm.
combination of wideband, medium band, and narrow band.
Right.
And so the narrowband filters are focused on recombination lines. So that
Mhm.
would be in the near infrared, that's Paschen alpha, bracket alpha. And then the medium bands are actually designed to target the polycyclic aromatic hydrocarbon feature at 3.3 microns.
Right.
And so they have these medium bands on both sides on, and then on to the left or the right, however you look at it, of that feature. So there are several programs who are employing all of the filters, as many as they can, to do this as best as you can do. Because even using all of the filters is still often, well, you get the full field of view of Webb, and you don't have to spend as much time as getting a spectrum. And so it's still cheaper potentially to use every single NearCam filter. At least the broad and the medium. The narrow bands, you start to significantly lose throughput, and therefore it starts becoming costly to do observations. But with the medium and the wide bands, the idea behind them and where they were created was so that one could sufficiently disentangle contributions from dust and PAHs at a level that was satisfactory for the science goal. So yeah, the answer is we hope so, yes. And some of the early results from FANGs and indeed goals, we're finding that, and I didn't show the actual data of the photometry, the spectrophotometry of the clusters, because it would take me too long to sort of explain the messiness of the plot, but we're finding that with only the filters in the early release science program, which again was not necessarily just focused on clusters, it's focused on all of the kinds of aspects of these galaxies. So the black holes, the clusters, the outflows, the merger, everything, the dust. It was meant to sort of be a coarse sampling of the instrument's capabilities. So the goals program got spectra, we got photometry, we got near infrared, mid infrared, all the instruments. And so we only have a couple of wideband filters and the medium band around the PAH. So we are much more limited in our ability to make very, very detailed statements about the properties of these sources that we identify. But that's also part of the follow-up in the cycles 1 and 2 and 3 to get more data to improve our ability to do that. I mean, it is possible, but with only the wideband filters that are in some of these early release programs, it's not really easy to disentangle the two, as you say.
Okay, thank you. Any other questions?
Well, yeah, I had my hand up for a while.
We don't see you. Oh, there you are.
Hello. Yeah, when you're using the nearby galaxies as proxies for the distant galaxies, so you can gain insights. And the problem is when you're observing the nearby galaxies with the James Webb Space Telescope, you're not observing the same rest frame wavelength bands as the distant galaxies. So how do you know the comparisons you're doing are valid?
So we're not making direct comparisons necessarily. I think what I'm more meant to say is that we find that these high redshift galaxies have very high star formation rates. You know, the early discovery of them at redshifts 10 and higher have redshift star formation rates in the hundreds. So they're not like Milky Way with a star formation rate of 1. You know, they must be these kind of more extreme systems. And we think that they must be likely, you know, mergers, many of them. And so the idea is not that we're studying their same wavelengths, is that we're studying the same system. If you were to take that system and bring it all the way forward, it would look like one of the, well, it would look like BV114. And so when you find a galaxy at redshift 13, they're not using the same bands as us. They're using they're using the mid-infrared bands, because the light that we're detecting in the rest frame is redshifted all the way into the mid-infrared. And in many cases, they're actually looking at optical light. And so like Hubble, basically, all the way out in the mid-infrared. So it's not a direct comparison, but
it's just that if you were to take, if you were to take one of these nearby galaxies and you're moving it into the distance, at the same distance as these distant galaxies, and then observe them with the James Webb Space Telescope, you would be observing them in the optical or the UV in their rest frame.
That's right.
So my point is that you want to choose proxies that are somehow the same as the ones you're observing the distance. So if you did move it into the distance, would it look the same as the distant galaxies? And if it didn't look the same, how do you know you're making a valid comparison?
So the galaxy still has light. So a high redshift galaxy still has young stars. It still produces light in the UV. It still produces light in the optical. We just can't see that light. So the stars are still forming like they would form in a nearby galaxy. So I'm not entirely sure I understand your question. It's true that, like, for example, on the left-hand side, this is like optical and UV light. If you took this galaxy and you redshifted it, it would look like a small red blob. But again, what you're detecting a high redshift galaxy and saying it has a total star formation rate of 100 is not the same as discovering all the individual clusters in a nearby system. And the reason I'm saying that they're similar is because they have similar star formation rates. Not that they look exactly the same, is that they are the only systems in the nearby universe that form stars at the levels that we know high redshift galaxies do. So they're the only kinds of systems that you can look at high resolution that would mimic the conditions of star formation at high redshift. Maybe not, maybe those galaxies don't look like these kind of crazy train wrecks, but they at least form as many stars as these galaxies do. So there has to be similarities in the properties of the gas and the dust, and that's kind of where we're going with the physics of it.
Yeah, sure. I was wondering about those diffraction spikes. Do you have ways of dealing with those diffraction spikes? Do you have some deconvolution mechanism algorithms, or are you able to observe the same object with a different orientation so that the diffraction spikes aren't in the same place?
Yeah, great question. There's multiple ways that you can deal with it. One thing that people have been doing for years, pre-flight even, is modeling the wave pattern of Webb. And so there's software and code and lots of databases of models for what this pattern is supposed to look like at every single wavelength, with every combination of dithering and kind of observing strategy that you might want. So you can take your exact same observing setup and you can simulate what the diffraction spikes would look like. And so that's what's been done a lot in the early papers, to sort of model and then subtract out the diffraction spikes. Obviously, that's not perfect because the models are simulating the wavefront sensor. And like, for example, when Webb first opened up, a rock hit one of the mirrors. And so it's not going to be perfect like the simulation is. And so the only way to deal with that is to use stars in the image. If you have a wide enough field image and you have stars that have the spikes, is to actually sort of basically fit polynomials or whatever, structure function you want to fit to the individual sort of 2D patterns of the spikes, and create an empirical model for what the diffraction spike looks like within your own image, and then use that empirical model to then subtract it off the spikes like you see in the eastern nucleus. And so it's a messy job, and for the people who study black holes, it's one that I don't envy.
Yeah,
Is that the
I would
source
just
of
think that there is a way to actually test that. Is if you could have a special, well, maybe not you, but someone could have a special project where they observe the same source at different orientations, and then test that idea, see if that deconvolution works properly.
Mhm.
Yeah, there are entire programs dedicated to sort of calibrating these kinds of things, as you say.
Right.
Yeah, and that's a lot of that work falls not necessarily on like observers. Like all this data was part of the early release science, which is actually all publicly available as soon as it's taken. And then now, a lot of the data that's coming in now is part of the cycle 1. So this is all guaranteed observations from astronomers around the world who proposed for time on the telescope. And that data is very often not available for at least a year. And actually, the cycle 2 proposals have already been put in. And so we should actually hear back about what the next 2 years of the telescope is going to look like soon. And all of this kind of calibration data is often under sort of director's time, or the instrument teams themselves get time to do these kinds of calibrations. So it's all publicly available, or it would be,
Right.
but it doesn't necessarily fall on the scientists to collect it. The observatory will set aside whatever time they feel that they need to do those kinds of tests. So yeah, it's a great question. It's definitely a big issue.
Right, thanks.
Okay. I think you explained the calibration. Apparently there is some sort of discrepancy which people have found early on with the calibrations. Has that ironed out yet?
It probably depends a little bit on what instrument you're talking about. The calibration for near cam, the near infrared imager, like
Yeah.
you see, like with the image on the right, I would say that back in October, they had probably a 20% error, and now they're probably down to a 5% error.
Okay.
So they're getting better, definitely in that direction. I would say the mid-infrared imager is probably at 10%, maybe better, 6-7%. The spectroscopy is where a lot more of the problems lie. The mid-infrared spectroscopy, I think, is fairly well calibrated at this point. It's the near-infrared spectroscopy, which is actually interesting because a lot of the early high redshift results have been using the near-infrared spectroscopy. So one might worry, actually, that things are
That's like for the redshift and all?
Yeah. Yes. So, there's always the possibility that we're maybe misinterpreting things, especially maybe when it comes to not necessarily where the line is, but the slope of the continuum underneath the lines, which tells you something a lot about the properties of the galaxy. So, yeah, I mean, I think that there's probably still a lot of work to be done there. And there's already been examples of people claiming detections of high redshift galaxies with early JWST results, and then some of them have been followed up with ALMA, right? So it's a totally independent millimeter array where you're essentially targeting to find a molecular line at that redshift, and so far several claims of redshift 13, 14 galaxies turn out to be redshift 4, 5, 6.
Yikes.
With ALMA. So it's not perfect. And it's probably going to take another year or so to iron everything out, probably.
Thank you.
I think there were just some results that came out within the last like 48 hours of similar things. So that might fall under that same umbrella there, Sean.
Yeah, yeah, yep, yeah. Yeah, like I think one of the really early results from the GLAST early release science program, they had said that there was a Redshift 14 galaxy that I think it's a Redshift, they just confirmed it at Redshift 5 with ALMA, and it's a relatively extraordinary Redshift 5 galaxy. Because it has a pretty unique set of properties that made it masquerade as a high redshift galaxy based on its spectrophotometry. And so, the argument that people are making is, well, even if it's not high redshift, it's probably still cool. And, we'll maybe learn something about the intermediate redshift galaxies now. And yeah, so the literature is kind of moving all over the place right now. There's, detections and then some rebuttals and, how many are we finding and what redshifts they are and what does that say about galaxy formation and, are there too many galaxies forming too quickly or not enough? And, are our models for cosmology wrong or not? All that stuff is stuff that will take a while to figure out, even if people want to write papers about it, already.
Well, it is quite a foment, and it's not surprising given such a magnificent instrument, which all of us taxpayers spend about $3.40 a year to support. I think it's a pretty good bargain. So our hour is up, Sean. I want to thank you so much for coming and sharing what you know about the James Webb Space Telescope and the buried treasures in nearby galaxies. So thank you all, and to all a good night.
Thank you, Sean, for sharing.
Thank you so much, everyone. It was
Have a
great
great
getting to
week.
talk to you. Yep. Have a great weekend.
Bye. Thanks.
All right, so long.